last section then of chapter 3. This is where we wrap it all up. Taking all of this time, not really a lot of time, 3 days to look at what do we do with inequalities of absolute values and polynomials, how we graph them, look for systems, and now we're going to apply it. All right, so there are a few definitions you're going to need to know. One of them would be this thing called the feasible region. When we're talking about all these inequality systems that we graph, and then we find where they have a common shaded area, that shaded area, and this type of problem. It's called linear programming because we're going to be graphing linear inequalities. There are times when you don't have linear inequalities, but this stuff we are. So the shaded area that's generated from the overlap of these different inequalities creates this feasible region, and this feasible region in industry would be an area that they would look at to discuss minimizing or maximizing something, a profit or a cost, something along those lines. So the feasible region, the shaded area, is made up of a various number of inequalities, and the hardest part about this is you're going to have to create those. And once we create them, you're golden, sort of, as long as your graph is good. If your graph is good, you see a good shape. If your graph is sloppy, it's easy to get in trouble with this stuff. And then we have these points. We call them corner points, and these corner points define the vertices of the the polygon. So we have that yellow polygon. It's a quadrilateral. And there's a fourth corner point, this last one down here at the origin. But we usually just chuck that one out the window in terms of consideration because we don't usually produce 0 items of something. And that's what that would represent, producing nothing. So we're not going to consider it. Although it is a corner, it defines my area here. Now, this particular example is in quadrant 1, and all of the things that we're going to be doing, constraint-wise, this is what these things are. The constraints are what define your linear inequalities. The constraints are always going to be in quadrant 1, and let's talk about why. So here's our example. We are manufacturing bicycles. We produce hybrid road bicycles, and then we produce mountain bicycles, right? So 2 types. Why would one of our constraints have to say something about X? Let's say X is referring to a hybrid bike. Why would one of our constraints have to say that X's must be greater than or equal to 0? Why do you think that would? Yeah. I can't produce negative bikes. If I were doing that, I wouldn't make any money, right? And it's not possible. I can't produce negative bikes. So I have a constraint for each of my 2 variables here in the sense that I've got the hybrid bike and the mountain bike, and each of those I have to produce more than nothing to be able to have any sort of a profit possibility. And so these 2 constraints, X greater than or equal to 0, Y greater than or equal to 0, are the very first 2 that you should start off in these problems. You could have 3 constraints. You could have multiple constraints on a given problem. But those are the first 2 we need to begin with. So that's why we're in quadrant 1. I can't produce negative items of something. All right, so we have a feasible region, the shaded area. We have corner points, these intersections between inequalities, or just X or Y intercepts. They define this polygon region. And then the constraints are your inequalities that you create. So that's what constraints are. They are your inequalities that you're going to create and you're going to graph them. So this next part down here is our process that we will use when doing these types of problems. We defined our variables, although we didn't write it down, but we said that X was referring to, in our case, the hybrid bike, and Y would refer to the mountain bike. Then we would determine what our constraints are going to be. Now, this, again, is where I start out with X is greater than or equal to 0, Y greater than or equal to 0. And then I have to figure figure out, based on the information that's been given to me in the problem, what my other constraints are going to be. Usually, there are some constraints that refer to the total number of items that you can build. If I'm a factory, I can only build X and Y numbers of things in a given day, right? And I can only work so many hours as an employee, and I can only have so many dollars per something as a cost. And so I'm going to have some constraints here that are going to be oftentimes tied to money in some sense, and then also oftentimes tied to a number of items that you're producing. So we find these constraints, we graph them, we shade them, and we determine the feasible region would be this third step. Separate from that, we're going to have some information given to us regarding determining this next part, this expression whose value is going to be used to minimize or maximize. So I can be finding, say, a maximum profit. I could be finding a minimum cost to producing something. And the expression that we generate will also be information that has been given to us in the problem set. We come up with that expression. We find our corner points. We use those XY values. We plug those XY values into our expression, and bam! We get number 6, the selection of the greatest or the least result, depending on what we are looking at. So that's our process. So what makes this difficult, challenging, is that we have to find these inequalities on our own. They aren't given to us. It's good that it makes you think, right? Can I advance? So you're still writing that stuff down right there? Yeah. We'll go ahead. Okay, so corner point principle is using those vertices to define our polygon. Those x and y values we would plug into this expression that we generated to come up with our max or minimum. That's all the corner point principle is. Let's move. You don't have to jot that down. If you don't get it down, go check out Blackboard. Actually, it'll be a YouTube post now. It won't be a Blackboard post. So once I let you know where it is and everything, you guys. All right, here we go. First one. Factory producing shirts. Long sleeve shirts, short sleeve shirts. And we have 30 minutes of labor for the short sleeve, 45 minutes of labor. Now here's what they need to do. They just need to produce all long sleeve shirts and then get some scissors. That's, that's it. Anyway, they don't do that. So we got 30 minutes of labor for the short, 45 for the long. 240 total hours of labor each day. So what does that mean to have 240 hours of labor? Give me an example of what that might mean. Not in an equation sense, but just, do I have 240 hours in a day? Okay, so what does this mean? I have what? I have employees. How many do I have? Does it tell me? Doesn't tell me. It doesn't tell me I have, but I have more than, a couple, because let's say I have 30 employees and they each work 8-hour day. Well, then there's my time. All right, anyway. Does anyone notice a little problem, perhaps, that we would come up against if I'm not careful, just in that first little bit of information about time? You know this problem? Bingo! We've got minutes for the labor rate per shirt, and then we have total hours as a day labor rate. And we cannot mix our units, so we have a choice to make. We either make everything minutes, or we make everything hours. So we're going to go hours. We're going to make 30 minutes become hours. We're going to make 45 minutes. So how many hours is 30 minutes? A half. How many hours is 45 minutes? 3/4, right? So you got to be careful of your units. Check those out. Minutes, hours. That's an oops. We got to convert them all. So we'll take 30 minutes, and that's a half of an hour, and 45 minutes is 3/4 of an hour. Now we're going to be ready to go. So that was an important catch right there. Now, also about that information is all of them talk about something relative to time, which means those three numerical values, 30, 45, 240, are all going to be in one of my constraints. They all talk about the same thing. And then we have some other information given to us. We talk about the maximum number of shirts. So there's going to be another constraint. There's my quantity of items. No more than 400, which means I can produce a maximum of 400 shirts in a day. And that was it in terms of what was given to us. We knew time of labor and total hours, and we knew how many total shirts. So let's go from that information and build our constraints that we're going to use to create our inequalities. Then we'll come back to this part A and B in just a second. All right, so what are our constraints? Okay, give me the first two. Always. What are they going to have to be? Okay, X is going to be, Y is going to be. Now, it makes me realize that I forgot something. What have I forgotten to do right now? Huh? Well, we're going to do that, but I have forgotten the important thing. Define the variables. We have not defined any variables yet. So X is equal to the number of short sleeve shirts. Y will be the number of long sleeve. Let's abbreviate these things instead of S. So, we're just going to do SS and LS. There we go. There, now we've defined our variables. Now let's go to our constraints. And I heard somebody say our first two should say we can't produce negative numbers of shirts and item type. So there are our first two constraints. Okay. I'm gonna be color coding stuff here, people. Color coding. Come on. There we go. Oh, no. Okay. So let's talk about our third constraint. This one, we will use the information given to us regarding the whole time thing. Who thinks they have it? Tell me what that inequality is. Really? Julie's right on.
Is it X less than or equal to 4?
Oh, you're close. That's one of them. So, I mean, that's a part of one of the constraints, but that's not quite it. Because if that was true, what are the only shirts you would be producing? Short sleeve. Do we produce only short sleeve shirts?
Oh, X plus.
X plus Y. That must include X plus Y. So, yeah, that's one of our constraints, that the number of short sleeves and the number of long sleeves must be less than or equal to 400. All right. Now let's go back to the time one. I've got information that tells me minutes of labor, we converted to hours of labor, and that's a per shirt number. Every time I got a per something, that always has to get tagged with a variable. So those numbers have to have variables attached to them. Think you know that? Now,
25X plus 0.75Y is less than.
okay, so 0.5x plus 0.75y is less than or equal to 240. Very good. So we got, time, number of items for the blue, and then our two just generic constraints, we can't produce negative shirts. So we've now limited ourselves to this first quadrant. That's the hardest part of all this stuff right there, is coming up with constraints. Once you get these, this is the easy. All right? Before we move on any further, any questions regarding where our constraints came from? They do get a little more challenging than this. The next one we're going to do is actually a lot more challenging. Only in the sense that I've got some multiple constraint things going on. All right, so here's what I've got. I have the following. I've got this graph. x plus y equals 400, and then I've got that graph, 0.5x plus 0.75y. And how did I find those? Cover-up method. These are standard form. Cover up x, find the y-intercept, 400. Cover up y, find the x-intercept, 400. It's connected. Cover up x, find the y-intercept, 320. Cover up y, find the x-intercept, 40. So I'm just doing standard form, finding intercepts. That's how I get these two lines, or these two lines. They're both solid because our boundary line is solid because it can be or equal to. All right, and I do have my x greater than equal to 0, my y greater than equal to 0. That's just defining that x and y axis. So now we shade, and we see where our feasible region is. All right, going with the blue. It's supposed to be less than, meaning I can test a point, 0, 0. Is 0 less than or equal to 400? Yes. So far my shading is on this side of the blue line. We do the same thing, 0 less than 240? Yeah. So I'm shading on this side of the red line, which means our feasible region is the overlap of the two. And that's where this comes from. Right? All of that area is my feasible region. What does that mean? What is a feasible region? Well, that's all of the values of shirts, long sleeve and short sleeve that I could produce that would fit all four of those constraints. How are we doing so far? Any questions? Pretty simple. All right, now we got to go to the A and the B part. So we've done the hard work. We found our feasible region. We have some points we need to create. We need to create our corner points. Here they are. Corner point right there at 0, 320. We have a corner point right there. Uh-oh. I got to find that one. And then we have a corner point down here at 400, 0. Okay, so who's gonna tell us how to find that one that's hanging out in the middle? Do I guess? Do I look at the graph and I say, it's about that value of x? Do I do that? No, because I don't know if my graph is really that accurate. So how do you find where two lines intersect each other? You have a system. We set up a system and we see what are the x and y values where they both have the same value. So we do that, set up our system. X plus y equaling 400. 0.5x, 0.7y equaling 240. And then probably it would be best to set this thing up and do elimination. So what if we got rid of the move over. Hello. We're going to multiply this guy by negative 0.5. I'm choosing to get rid of the x's. You can choose to get rid of the y's. So this becomes negative 0.5x minus 5y is equal to half 200 is 200, but it's a negative. So there's my new equation that I get, and then I can find out my answer. 0.25y is equal to 40, and if I divide by 0.25, I get 160. All right. We now know the number of long sleeve shirts, right? Y is long sleeve shirts. So that is number of long sleeve shirts. X would then be found probably easiestly. That's a new word I invented. Easiestly. You would plug in 140 into here, and I get x plus 160 equals 400. So x is equal to 240 shortens. There we go. We have found the missing corner point. 240, 160. All right. Questions now? Anything? Yes?
So where the intersect is the amount they're gonna.
Where they intersect is the amount where they're producing the same. Yeah. In terms of our inequality goes, right? It's the break-even point. Any other questions? Okay, so what do I do with those corner points? Well, that is now where this next part comes in. Let's take a look at part A. We've got the profits on a short sleeve shirt and long sleeve shirt are $11 and $16 respectively. Find the maximum possible profit. All right, so a couple things. $11, $16, those are a per shirt cost, which means I'm going to have some variables attached to those. Then I'm looking for a maximum profit. So we have to come up with an expression that we will then use to create an equation that talks about profit, that I will then go and use these corner points. What do we have? What's our expression? What's our profit going to be equal to? How are we going to find our profit for the day? Exactly. If profit is equal to the dollars that I make per short sleeve shirts and the dollars that I make per long sleeve shirts, there's my expression, which becomes an equation when I say it's equal to the profit. That's the part I need to be able to answer the what is the maximum daily profit. So this is the next component here. This is that expression that we use. Now what we do with that expression is we come down and we set up a table with these corner points that we found. So our table might look like so. Corner point values, profit. All right, let's go find our corner points. First one is 0 and 320. So what that means is I'm not going to produce any short sleeve shirts. I'm only going to produce long sleeve shirts. Yes, sir.
Are you using the corners for the maximums?
I'm using the corners, good question. I'm using the corners because they define this polygon, which is my shaded area, which is all of the possible values I could have to make this maximum happen. Yeah? All right, then I'm going to use my 240 or 160 number. There's my corner point. And then my last one is I don't produce any long sleeve shirts, and I only produce 400 short sleeve shirts. So I need somebody to crunch some numbers there. Actually, you don't have to crunch the numbers. I know what they are. But so those are what I'm going to test. Now, I could test anything inside of this yellow area. However, those are going to be smaller XY values, which means I'm not going to be maximizing my count. I'm out on the limits of my polygon right now. Those are where I'm going to see where I can have a maximum. All right, if I plug this in, you guys can check to make sure I'm doing this right. But I think that the profit you would get if you sell any short sleeves and only sold long sleeves, I think it's $5,120. I believe this one is $5,500. $5,200. Did you just say get it? Did you just say get it right? Did you just say that? All right, and then this one, I don't remember what this one was. What was this one? Say it again. 4,400. All right. Okay, so again, that's the money I'm going to make with those combinations of shirts. And we can see that there's my max profit. And then I would be able to state for answer, my max profit is going to be found at $5,200 when I sell 240 short sleevers and 160 long sleeve shirts. All right, what about part B? This is a good part. So it's also wise of us to not only be able to crunch the numbers. But let's now go a step further and be able to explain what we might find with this whole feasibility region thing. So the second question is why the factory manager might decide to produce different numbers of shirts than the ones giving the maximum. Why? The math tells you that you're going to make the most money when you sell that many short sleeves and that many long sleeves. But why would a manager consider saying, I'm not going to do that? Yeah.
Like seasonal, like summertime, summer.
Exactly. This is a daily thing. What if you're in the middle of winter? Right? You're probably going to want more short or long sleeves than you want short sleeves. So that might skew your number. What is another reason why maybe you're going to pick something different? It kind of goes along with this. Supply and demand. Exactly. Maybe people don't like the short sleeve shirt because you did it my way and you made long sleeves and they just cut out the short sleeves, so one sleeve shorter than the other. They don't look cool. They don't look as good. Again, it goes back to what's being supplied versus what people want. So those would be some contributing factors. Something could consider. Now, there are cases where the maximum might be found on one of those corner points where you're like on an axis, where you don't produce any whatevers. And mathematically, again, it's telling you that's going to give you the largest number, but as a business owner, if you're producing these things, you've spent money to pay for the labor and the machines that make those short sleeve or those long sleeve shirts. And if all of a sudden you're not producing any of them because you see mathematically that you're going to make more money just making the other type, well then you've got wasted time and resources sitting on your factory floor because the machines are idle. They're not doing anything. So all these things kind of contribute into the decision process. So mathematically it says to do this, but I might not want to do that because of the feelings. Yeah.
Why would the corner points be the maximum?
Well, there could be a case where maybe this thing on the polygon side stretches way out here in some X values. Maybe I have, I don't know, 180 shirts. And it just so happens that at the cost per shirt, profit-wise, that might give you the biggest number. So the answers for these are not guaranteed to always be the point that's kind of hanging out in the middle. It could be one of these points on the ends. And that's why we do the table. That's why we test our table and we see what values.
But why could it not be like the inside of the yellow?
Oh, good question. Why can it not be the inside of the yellow? All right, let's pick a point inside here. Let's pick 120 and 40. Plug it into our equation. And let's see what kind of profit we make. Somebody do that for me. Do you have that number yet? Is that right? Or you got a bigger number? 1960. Great question from Alex. Why wouldn't we want to use something like that? Well, again, mathematically speaking, I am not anywhere close to the money I could make. So let's look at it just graphically. If I have this big area, and those outsides of my polygon are going to be like the limits of what I can produce. Don't I want to produce at the limit? Because if I'm producing less than that, right? Now this is a maximizing problem. We're also going to have a minimizing problem where my shaded area isn't backed up against the origin like this. It might be out here somewhere. And now you're looking at points that are on the lower side of my polygon. Does that answer your question? Any other questions here for this one? All right, let's take a real quick stretch break, and then we'll come back to you guys going to try one on your own. So this information here, salary, 35 for a nurse, 18 for a nurse's aide, is not a part of our constraint. That is going to be the expression that we use to answer the question of minimizing salary costs. So for for right now, we'll just stick this off to the side. What is it? 18 bucks. We define our variables, so we're going to say x equals the number of nurses, y equals the number of nurse aides. Okay, then we're ready to now come up with our constraints. We can hire up to 50 people, but need to hire at least 20. Okay, let's talk about that part. Up to 50, need at least 20. The people is made up of the nurses and the nurses. So just that information gives me a constraint that says that I have the number of nurses and nurses aid. Maxes out at 50, that has to bottom out at 20. You could have written that as x plus y less or equal to 50, and then a separate inequality x plus y greater than or equal to 20. So this just becomes easier when you write it as an and problem. All right, so let's we're going to kind of come up with our constraint and then graph them as we go. So this constraint would look, I'd have two lines. Both of them are in standard form. Let's see, there's one of them. There's the other one. So there's my constraints on the number of people that I can hire. All right, moving on to what's our next item of business here. We have the head nurse wants at least 12 aides. Okay. At least 12 aides. And then this number of nurses must be at least twice the number of aides. We'll do that one separately. So let's talk about the at least 12 aides part. So if aides is y, that means y must be greater than or equal to 12. That means I have a line right there. I'm trying to color code it. Sorry, got the wrong color. Now, there's kind of another constraint we could come up with right here because of the fact that it says we have twice the number of nurses as aides. So let me talk about how we would develop that one first. And it's a little funky when you read it. The number of nurses must be at least twice the number of aides. So it's meaning I want 2 times the number of nurses as I have aides. And it's easy to confuse it and read it the other way. But we want twice the number of aides, or number of nurses than aides. And so if X is our nurse, and we want to have at least twice as many, this means if y represents an aide, if I have 1 aide, I have 2 times 1, or 2 nurses. So there's my inequality for that one. Now we're going to change this so we can graph it in slope-intercept form. This is, if I just flip things around, it's 2y less than or equal to x, which means y is less than or equal to 1/2 x, which is a slope-intercept, right? That is correct. I want 2 nurses per nurse's aide. So watch. Y is nurse's aide, right? If I picked 1 nurse aide, how many nurses do I have?
You have it switched around.
What do you mean I have it switched around?
You have X as nurses and Y as nurses.
I think we're good. So Alex, you're wondering about whether this should say y greater than or equal to x.
1 nurse aide is going to need 2 nurses.
Right. So watch. 1 nurse's aide times 2 gives me how many nurses? No, gives me 2. 2 times 2. Huh? I need. No. I need 2 nurses per nurse's aide, right? So that's what I have. If I have 1 nurse's aide, I have 2 nurses. If I go the other way, so here's what I think this is what you want to do. You want to do this, don't you?
Yeah.
Okay, watch. If if I pick one nurse, how many nurses aides do I have? And I don't want twice the number of nurses aides, I want twice the number of nurses. So it's this guy. Because if I put one nurse in there, that gives me two nurses aides. Now I'm doubling on nurses aides, and that's a bad thing. I'd rather double on nurses aides. And I know it's a little confusing, right? All right. Go back to this. So graphing that y to 1/2 x is going to be that right there. So I have my constraints on the number of people. I have constraints on the minimum number of nurses aides. I have my constraints on the number of nurses. And now we're going to go ahead and graph these shaded areas and see what we get. So in between the green lines, I would be shading in between the green lines. And then on the blue line, I need to be greater than or equal to 12, which means I'm shading above. So far, I have shading going on in here, in between the green lines. I have shading above the blue line. And then I have shading, because it's a less than, I have shading below the red line. And so all that I am interested in, it looks to be right there. Yep. All right? So we have some corner points we need to consider now. We have that corner point, we're going to need to find it. We have that corner point, we're going to need to find it. And that corner point, we're going to need to find it. All right, so we go and we set up all of our systems now between the red and the blue. Let's go check out the red and the blue connection. That's not blue. That would be black. Red and blue. We have y equal 12 for the blue, and y equals 1/2 x for the red. We just simply substitute in. I get that 12 equals 1/2 x, or x must equal 24. So this connection has 24, 12 as its corner point. All right, 24, 12 right there. Let's go check out red and green. So what's going on with red and green? We've got green, which is x plus y is equal to 50. And then we have red, which is y equals 1/2 x. And we'll probably, I guess we'll just substitute in. We get x plus 1/2 x is equal to 50. So that's 1x plus another 1/2 x, 3/2 x is equal to 50. Multiply by 2 and divide by 3. We get x equals 33.3. Right? And that would mean y would equal 1/2 of 33.3, or 16.7. So that corner point is 33.3, 16.7. We're talking about numbers of people. Well, I can't take 1/3 of a person, or 1/7 of a person. So we'll see what happens, but it's probably not going to be a good one to look at. And then finally we get 33.3, 16.7. And then we get the red and the green, or the blue and the green. Go over here. Green. And once again, x plus y equals 50. And y equals 12. So we get x plus 12 equals 50, or x equals 38. And then there's our last corner point. And, you know, we're probably minimizing for thinking that that 2412 is probably going to be my number. I bet you're right. So we put in our table. We got our points, and we have our cost, 35,000 for a nurse, 18,000 for a nurse's aide, and we plug all these numbers in. So 2412. 33.3 and 16.7, and then 38.12. Now give me the numbers for these guys if you have them. What do we have for 30? Well, for any of them. First one.
That one is just
One what?
or 1 million.
That's a lot of dollars. All right, what's the next one?
Next one is 1,466,100.
Yeah, and
Last one is 1,546,000.
all right. So we can see that, you know, it kind of intuitively it made sense that we have the smallest value, 24 and 12 is going to produce my result. Now, maybe we had this answer, we had some of those stuff written down, and I said, you won't get any credit unless you show me all this stuff. And yep, that's true. If you don't show me the graphing, the inequalities, the constraints, I'm not giving you credit for it. Okay? Any questions on what's happening there? Did we answer all the questions first of all? Yeah, I think we did. How many nurses and how many aides should be hired to minimize the salary cost? Oops, we didn't really answer it. That I should hire 24 nurses.
12 aides should be hired.
12 aides. Well, there we go. In this case, we was. In this case, we were. And that is because it said, here's the big reason why, we were minimizing the salaries. Last one we were doing, we were maximizing. No. No, these feasible regions, you're usually finding out max nits. Yes?
So the corner points are the same where it all overlaps?
The corner points define the polygon that results from the common shaded area.
Alright.
Got it? Yes?
Will everything be quadratics?
Will there ever be quadratics? Because this is linear programming, we will have just linear constraints. But you can have, yes, but we won't. Ours will all be linears.